Welcome to Fuzzy Mathematics, the Basics. In the previous lectures, we have talked about fuzzy sets. We have talked about definition of them, notations for them, relations between them, and operations on them. We observed that the relations between and operations on fuzzy sets are defined pointwise in terms of operations on real numbers in the closed interval from 0 to 1. And the relations between and operations on fuzzy sets totally depend on the properties of the relations between and operations on real numbers in the closed interval from 0 to 1. Therefore, I'd like to transition away from fuzzy sets for the next several lectures. In this lecture and the following several lectures, we are going to talk about several types of algebraic structures with certain properties. But the discussion will not be confined to the fuzzy power set or to the closed interval from 0 to 1, but more generally. And in today's lecture, I'd like to move on to a new topic, partial ordered sets, in short, POSets. Let's start with the definition of partial ordered sets. What is a partial ordered set? A partial ordered set is a set together with a partial order. What is a partial order? A partial order is a relation with some special properties. What is a relation? Let X and Y be true non-empty sets. The Cartesian product of X and Y, denoted by this notation, is the set of all ordered pairs XY, where the first element of each ordered pair comes from set X, and the second element comes from set Y. A subset R of the Cartesian product of X and Y is called a binary relation from set X to set Y. A relation R from X to Y is a set of ordered pairs, or a collection of ordered pairs, where the first element belongs to set X and the second element belongs to set Y. Binary relations represent relations between the elements of the two sets. We often omit the word binary when there is no danger of confusion. Moreover, when the ordered pair XY belongs to R, element X is said to be related to element Y by relation R. We often use this notation to denote that X is related to Y by R. A relation from a set X to itself is called a relation on X. A relation on a set X is a relation from X to X. In other words, it is a subset of the Cartesian product of X and X. There are several properties that are used to classify relations on a set. A relation on a set X is called reflexive. If X is related to X for all elements in the universal set, a relation R on a set X is called symmetric. If X is related to Y implies that Y is related to X. A relation R on a set X is called antisymmetric. If X is related to Y and Y is related to X, implies that X equals Y. A relation R on a set X is called transitive. If X is related to Y and Y is related to Z, implies that X is related to Z. Next, the definition of partial ordered sets. A relation R on a set X is called partial order or partial ordering if it is reflexive, antisymmetric, and transitive. A set X together with a partial order is called a partial ordered set or POSet. And members of the set X are called elements of the POSet. We often use relations to order some or all of the elements of the set. For instance, we order the set of integers using the less than or equal to relation, which containing the pairs x, y, where x is less than or equal to y. Let's do some examples. First, example 1. Let Z be the set of integers is the less than or equal to relation, a partial order on the set of integers. Firstly, because x is less than or equal to x for every integer x, the less than or equal to relation is reflexive. Secondly, if x is less than or equal to y, and y is less than or equal to x, then x equals y. So the less than or equal to relation is antisymmetric. Thirdly, because if x is less than or equal to y, and y is less than or equal to z, then x is less than or equal to z. The less than or equal to relation is transitive. Therefore, the less than or equal to relation is reflexive, antisymmetric, and transitive. It is a partial order on the set of integers, and the ordered pair is a poset. Next, example 2. We use this notation to denote the set of positive integers. Is the divisibility relation, a partial order on the set of positive integers. Firstly, because x divides x whenever x is a positive integer, the divisibility relation is reflexive. Secondly, if x divides y and y divides x, then x equals y. So the divisibility relation is antisymmetric. Thirdly, if x divides y and y divides z, then x divides z. The divisibility relation is transitive. The divisibility relation is reflexive, antisymmetric, and transitive, so it is a partial order on the set of positive integers, and the ordered pair is a poset. Another example, example 3. Is the inclusion relation a partial order on the power set of x? This symbol denotes the power set of x. Firstly, A is a subset of A whenever A is a subset of x. So the inclusion relation is reflexive. Secondly, if A is a subset of B and B is a subset of A, then A equals B. So the inclusion relation is antisymmetric. Thirdly, if A is a subset of B and B is a subset of C, then A is a subset of C. So the inclusion relation is transitive. The inclusion relation is reflexive, antisymmetric, and transitive. It is a partial order on the power set of x, and the ordered pair is a poset. In different posets, different symbols, such as less than or equal to, divisibility, inclusion, are used for different partial orders. However, we need a symbol that we can discuss the ordering relation in any poset. Customarily, the notation less than or equal to is used to denote that x is related to y in an arbitrary poset. This notation is used because the less than or equal to relation on the set of real numbers is the most familiar example of a partial order. This symbol is often used to denote a partial order relation in any poset, not just the less than or equal to relation. This symbol is used to denote that x is related to y, x is less than or equal to y, and x is not equal to y. In this case, we say x is less than y or y is greater than x. When x and y are elements of the poset, it is not necessary that x is related to y or y is related to x. For instance, the set of positive integers together with the divisibility relation is a poset. In this poset, 3 does not divide 5 and 5 does not divide 3. And this leads to the next definition. The elements x and y of a poset are called comparable if either x is related to y or y is related to x. When x and y are elements of x such that neither x is related to y nor y is related to x, x and y are called incomparable. That's one of the reasons why a partial order is partial. Here, partial is used to describe a partial ordering because pairs of elements may be incomparable. When every two elements in the set are comparable, the relation is called a total ordering. If this is a poset and every two elements are comparable, X is called a totally ordered set or linearly ordered set, and the relation is called a total order or linear order. A chain is a subset of a poset such that every two elements of the subset are comparable. A totally ordered set is also called a chain. In this lecture, we have talked about partial ordered sets. Next time, we will continue this topic. We will talk about representing relations using diagrams. Thank you.